All right, good evening, everyone. Okay, so so we're going to take a look at Module 4 and maybe Module 5 tonight as well. I also know that you guys would like a bit more examples. So, Module 4 has actually quite a lot of theory. So I think what I'm going to do is I'm going to do the examples in Module 4 that we can do, and then we're going to take a look at Module 5, which is kind of what I want to get at, because Module 5 also has a big theory component, plus it also has quite a bit of or rather calculations and stuff that we need to do there. And I'm afraid that we're not going to get enough time for that in one class. All right, okay, so you guys will see Module 4 is mainly measuring instruments and test equipment. So the focus of Module 4 is going to be mainly on things like analog to digital converters. Right, so this is pretty much what we are going to take a look at here. I'm not going to spend too much time here because I actually want us to do, to actually spend more time on some other chapters as well. Because there is actually quite a lot of chapters that's just basically reading, like chapter 4 is almost like that. And chapters 7 is also a lot of reading. So is chapter 8, but chapter 8 has a lot of calculations and examples that I would like us to work through. And then chapter 9 chapter 9 doesn't really have a lot going for it. But in any case, so chapter 4, I'm going to kind of skim through a lot of this stuff. Okay, so we're going to take a look at analog and digital converters. So essentially, we take an analog value. So usually your analog values are, an analog voltage, for instance, or analog current. It's continuously changing current, whereby digital, your changes are in discrete little steps, right? So associated with a binary value as well, or usually that is the case. Right, so you basically change one numerical value for, it actually still stays the same. Essentially, it's just displayed as a binary value. Right, so here's another example of it. So here we have a signal that's essentially changed into a digitized version of itself. And this is just to basically show what the difference between the two is. So again, an analog signal is a varying signal between two ultimate values and will change as time progresses, where a digital signal will vary between two definite values or two discrete values as time progresses. Now, what I do not agree with, and I believe this is actually from the textbook, is that digital only has two values, high value equated to logic 1 and to logic 0. I mean, you can have different levels, and then you can actually have binary numbers going up. That is if you have more than one digit. If you just have one digit, you can't really get any useful information from there. Okay, so our very first circuit that we have here as an analog to digital converter is the Schmitt trigger. So I've had, how can I say, experience with this one before, with the oscillators. And again, you essentially, so it's a circuit that's going to have two firing points or two triggering points and a low and a high. So if our input, so for instance, I believe our one trigger point sits here and the other sits there. So, but essentially, in this case, this circuit is now set up. The moment we get above the upper trigger, you're going to have conduction on your output. So your output is going to output high. So it's essentially taking your waveform and changing it into a a digital signal in a very direct manner. So, but also just in the form of high and low. There's no in between value here. And then the moment our circuit then goes below the low trigger point, that's where you're then going to have your output being driven low, right? And then again, when we go above the upper trigger point, be driven high, then again, driven low, below the low trigger point. All right, so this is pretty much what's going to happen with the Schmitt trigger. So Schmitt trigger is really helpful if you have a sensor, or rather you have a system or something that you want to measure, but the only thing that you want to measure is whether the thing is on or off, right? So an analog or a Schmitt trigger is really good for for applications like that, right? So if you want something just to show you on or off, you don't really care about any values in between, then this is the way to do it. Okay, so then there are different methods of analog to digital conversion. So there's direct compensation, voltage to time conversion. So I'm going to let you guys read through this. I'm not, like I said, I'm going to skim through this. We are going to take a look at a few examples on this as well. And then there's also voltage to frequency conversion. And yeah, so if we take a look at the voltage to frequency analog to digital converter, I still don't get how this is voltage to frequency, but okay. So essentially what we're going to get here is you're going to have three comparators. I believe this is actually, let me just make sure. I think this is actually direct compensation if I'm not mistaken. But anyways, but I believe the textbook calls it this. But anyway, so you have three comparators, and then you have a reference voltage that is then divided up into three other voltages. And yeah, so here you have your input, and yeah, so you're basically comparing your input to three different reference levels, and that's then going to determine the output of your comparators. Now, if your input voltage, so your analog in here, is between 0.25 of your reference voltage, you're going to have this comparator here then outputting a 1, and the other two going to output 0. And if your reference is, or rather your input is between 1/4 of your reference and half of your reference, which is right there, so that's going to activate comparator 2. So that's essentially then going to output 1 there, 0 there. Oh, I said actually below, okay, below 1/4 of your reference, actually it's not going to activate that C1. I actually see that now. It's going to be 0. Sorry about that, guys. That's going to be 1, 0, 0. And then the next part, yeah, that's when between half and 3/4 of VS, that's actually then going to activate C2, and voltage actually high enough. And then for all values above 3/4, meaning the voltage at this point is higher than the voltage, or rather the voltage going in from the analog input is higher than the voltage on the reference, or as our reference, that's then just going to output 1s throughout. Okay, and this is now actually our first example that we can take a look at. And this is a digital to analog converter. Now, digital to analog converters does the exact opposite that what an analog to digital converter does. So here we take a digital value and change it into an analog value. Right, and so how we do this, we again, the most common way of doing this is what we call the R2R type digital to analog converter. There are other types, but this is probably the more common one. And yeah, so we have a 4-bit digital to analog converter here. So what you guys need to know is that value there is your A, that's your B, and then the next one is C, and then the next one is D. Yeah, in fact, I actually corrected this example. In the textbook, they fill it in backwards for some reason. They have A as the first one, which doesn't work that way in reality. It works this way. So A, B, C, D, and yeah, so A is going to be your most significant bit. So that's obviously going to carry the highest value. And then D is your least significant bit, which is then going to carry the least value. Right, so that's what the formula for your output voltage is going to look like. And yeah, so you're also going to have your reference voltage, which is not shown here because, oh yeah, wait, your reference voltage, yeah. So your reference voltage is just basically how it is actually done is you're going to have your Vref voltage applied. And so essentially through switches or transistors, you're going to have that then applied to the R2R ladder. Okay, and this is then going to give you, so the output voltage is then just going to be 10.3125 volts for this particular example. All right, so that voltage then is going to represent 1011 in binary or 11 in binary. Right, and so this basically depends on what your reference voltage is. Yeah, so if your reference voltage was 16 volts, you would have gotten 11 volts read out as your analog value. Okay, and then we have frequency counters. So frequency counters is actually, all of these are pretty much analog to digital converters. Right, but they, yeah, so, but these are also mainly, how can I put this, ways to implement digital voltmeters. All right, so if you take a look at the frequency counter, essentially what it does, it basically, yeah, so it's a device that's used to measure frequency, and yeah, so essentially the counter here is dependent on two signals. You're going to have an input signal and a control circuit signal. So essentially what happens here is you're going to have your input here going into an amplifier. That then drives a Schmitt trigger that is basically going to give you a square wave pulse like that. You're going to have an AND gate, and then you're going to have your control circuit with a time base and a gate control. So your control circuit here is basically going to give you then a fixed time period, or a pulse with a fixed time period. And then essentially what this thing does, the AND gate is now going to basically output these pulses within this time period from your control circuit. And based on how many pulses that you get within one control circuit pulse, that's then going to be counted. And that's then basically going to give you a frequency readout, right? So the control circuit will usually have some fixed time period. So let's say this is, for instance, a 1 second pulse, just to make things a bit easier. So that's a 1 second pulse, and your counter counts, let's say 50 pulses in that 1 second, then you have a 50 hertz signal that you're dealing with. So yeah, so it's actually quite nifty. It's not too difficult to grasp, I think. Okay, and that's pretty much how frequency counters work. And yeah, so this kind of is implemented in the next few circuits that we're going to take a look at, but you also get the one that we have as a frequency to, or voltage to frequency converter, which is essentially an analog to digital converter. So you have an unknown voltage here at the input. You have an integrator, and this integrator is essentially then just going to output a triangular waveform That's then going to be fed into a comparator. So you actually, yeah, so what is missing here is a reference voltage. And yeah, and that's then going to give you a square wave output there. And that square wave output is also going to drive a precision pulse generator. So it's essentially going to keep the integrator generating little triangular waveforms. And this counter is pretty much just going to then keep on counting the pulses. Yeah, and that pulses, yeah, those pulses are then going to be generated at a specific frequency, depending on the input voltage. Right, so that frequency is then directly proportional to the voltage that we having there on the input. Right, so this is a way of measuring the voltage, but in a time or frequency base. And then we also get, yeah, so this is now where we're actually going to get into the digital voltmeters. First one that we have is the continuous balance digital voltmeter. So it's again, it's still an analog to digital converter, but this one actually makes use of a digital to analog converter as well. So essentially what we're doing here is we have some unknown voltage that we want to measure, so V1. Now, essentially what happens here is, so as long as V1 is bigger than V2, the comparator here is going to output high. That's going to keep the AND gate, so the one input of our AND gate is going to be triggered high. And then we have a clock pulse generator here. So the AND gate's essentially going to generate a bunch of clock pulses. And then our counter is going to increment on each pulse. And the counter value is then sent onto the digital to analog converter, which takes the digital value that's stored on the counter and changes it to an analog voltage. That's then again applied to the comparator and compared to our unknown voltage that we're trying to measure here. Now, basically at the moment, yeah, so while V1 is bigger than V2, this whole process will just continue. Counter will continue counting the pulses from the AND gate, and the digital to analog converter will convert the value on the counter to an analog voltage. And yeah, so the counter will continue doing its thing up until a V1 and V2 are equal to one another, at which point the comparator is then going to output 0. And now the AND gate is not going to send out any signal. And that is then pretty much the value that you're then going to get for your voltage. So the counter is pretty much going to then digitally store your, or going to have a digital store, oh goodness, basically going to digitally store your V1 value there, and that's then going to, well, through a driver usually, going to be shown as a readout usually on some LED display. Stair slope voltmeter works very similar to continuous balance digital voltmeter. So again, we have a comparator with, again, an unknown voltage and an incrementing reference. You guys will see there's a mistake in the textbook. The textbook has a clock pulse generator there as well. So if you put a clock pulse generator there, it's going to do nothing. It needs to be a digital to analog converter, so D to A. So again, as long as the unknown voltage is bigger than your reference here, or your changing reference, you're going to output 1. So for VU bigger than VR. And that clock pulse generator here is going to generate pulses for as long as the comparator is outputting 1. And that's going to increment your digital counter. That value is going to be sent onto your digital to analog converter, which then will increment your reference voltage up until VR is equal to your unknown voltage. Then comparator is going to output 0, clock pulse generator is going to stop, and that's pretty much then going to be the voltage that you read on your display. That's going to be your unknown voltage. So yeah, so it's basically going to generate a graph like this over time, right? So yeah, so basically you have a reference that you increment over time, and then at the point where it's equal to your unknown voltage, that's when the process will stop and you will get that voltage shown on your display. And then we have the successive approximation voltmeter, or you can say successive approximation analog to digital converter. So yeah, so the drawing or the circuit in the textbook basically have a short circuit running here, so your unknown voltage is 0. But yeah, so in that sense, the thing is already done with what it needs to do. But if you take out that short circuit, then you put your unknown voltage there, then you're good to go. Anyways, so this one also, again, very similar to the previous two circuits. This one works a little bit differently. So essentially, again, VR and VU, yeah, I don't know why they say reference voltage here. That's the reference voltage for your digital to analog converter. But in any case, you have a changing reference generated by your D2A. So you are basically comparing VR and VU here. And when VU, so essentially what it does, when VU is bigger than VR, in fact, I'll actually do maybe an example here. So it makes use of a 4-bit. So this essentially this circuit that we're working with here, or rather the system we're working with here, we're mainly going to take a look at 4-bit values. It's easier to do. You can have more than 4-bit values. You can also have 8-bit values in your logic programmer as well, or even bigger. You get microcontrollers that can do up to 64 bits. So yeah. But anyways, so essentially, yeah, let me maybe explain with the example here. So essentially, you're going to start out with a whole bunch of zeros being stored in your logic programmer in the form of a binary value. Then essentially what happens is your logic programmer is going to, yeah, so that value is then stored in the register. So essentially, it's going to then increment that value by setting the most significant bit to 1. So if you convert this binary number now to a decimal value, that's going to be 8. So this is then going to represent 8 volts if you have a 1-to-1 ratio with the binary and analog value. And yeah, so in this sense, your reference voltage is still lower than your unknown voltage. Our unknown voltage in this case is 11 volts. So it's going to keep that 1. Right, so it keeps the 1, and then it moves on to the next most significant bit. And in this case, it now picks up, okay, cool, that's 12 volts. So the comparator is essentially now going to output 0 to the logic programmer. And it's going to then say, okay, cool, VR is now bigger than the unknown voltage. So it's going to reset that 1 that it just set back to 0. See that in the next step, in step 3. And then taking that, then it takes the third most significant bit, sets that to 1. That's now 10 volts, which is now again less than the unknown voltage. So we keep that 1. And then lastly, we set this logic programmer will set the register then to 1011, which if you convert this binary number to a decimal number, that's going to be 11 volts. And yeah, and that's then going to give you the reference is then equal to the unknown, and we then keep that 1. Right, so that's then going to give you, that's going to be the 11 volts then that you're going to see on your display unit as well. Right, sorry guys, I'm going fast through this because I actually want to get through some of chapter 5 as well. Okay, so the double slope digital voltmeter, there's a heck of a long explanation in the textbook as well on this. I just find that the textbook explanation jumps around quite a bit between when this thing is taking a reading and what this thing is actually doing. So it gets a bit confusing. The textbook kind of starts at the back end explaining how the circuit works. Right, so essentially what we have here, if I remember correctly, is, okay, so we have this integrator. So this integrator, so this capacitor is going to charge. So what is not shown here again is a reference voltage here that's there, well, that's a different type of reference voltage, but in any case, something that needs to be compared to. Or this thing is pulled to, you know what, I think this thing is actually pulled to ground as our reference in this case. So essentially, as long as this integrator is outputting something, and the integrator's output is going to look something like this. So if your unknown voltage here is a constant voltage, then your integrator is going to change that to a sloping line. So yeah, so essentially what's happening here is this thing is going to keep on outputting that sloping line. So you guys will see you have a clock pulse generator here. And as long as VU is applied to the comparator, essentially the capacitor there of the integrator is going to charge up to the unknown voltage. And what that's going to do is that's going to drive this clock pulse generator, and it's going to drive this counter. Just trying to remember, yeah, so there is a time associated with this as well. I'm just trying to remember how this works. So yeah, so this counter is going to keep on counting. Now, the counter, yeah, so essentially the counter is then going to count till it rolls over, right? So basically, depending on the bit value of the counter, it can count to. So let's say, for instance, in this case, it's going to be 9,999. Right, so it's going to take some time to get to that point, and then it's going to roll over. And then when it rolls over, it's going to generate a what we call a flag output that then can be used to drive a flip-flop, which can then in turn be used to drive a switch actuator here. So VR, so this switch here is now going to close there and open there. So essentially now, this is now going to discharge VR. And yeah, that's going to give you, so the counter is now going to count again. And the value that you then get from the counter, that's your unknown voltage. Right. So yeah, so essentially you're going to get two different times here. Yeah, it's a very, let me just get to the textbook, because the textbook explanation is not too bad, but it jumps around on what this thing is doing. Kind of starts at the back end on how the output is generated, and then explains what's going on. Maybe share my screen to the textbook as well. You guys can see what I mean. Okay, let's do this. Okay. Okay, so chapter 4. We want to get to near the end of chapter 4 here. So you guys can see there's not even an exercise on the successive approximation voltmeter here. In fact, I think maybe I'll demonstrate with a different value as well. Yeah, so there is a bit of a typo in the textbook as well. So they say T2 here, that should be T1. Actually, commented there. So yeah, so as per, okay, yeah, so basically that capacitor there, when the unknown voltage is applied, will charge during T1. And that's going to be governed by the magnitude of the unknown voltage VU. So the gate is then open, clock pulses will be generated by a clock pulse generator. They're fed into the counter and they will count through the full capacity of the clock pulse generator of 9,999. And the time duration of this is determined, and a transfer pulse is fed to the flip-flop, and that will then throw the switch actuator here, and that will then switch to the reference voltage. And yeah, so now the capacitor C will then discharge to 0 during time interval T2, while the counter, which had set to the commencement of time 2, will start counting from the start again. So this basically, yeah, so this counter again, that had reset. And yeah, so as soon as the capacitor is then discharged, the comparator will close the gate, which forces the counter to stop counting, and the unknown voltage will then appear on the display. Right, so basically the counter will then show, yeah, or the display unit will then show the value. It's not super, yeah, so the textbook doesn't really make super clear how this thing exactly works, but yeah, but this is what you guys pretty much need to know. So it's from here. So you guys can see they kind of start on the back end here. So essentially the two time intervals that we have here, T1 and T2, will be proportional to your unknown voltage. Right, so this is essentially voltage to time conversion that we're doing here. In fact, yeah, so the weird thing is we talk about the ways to convert voltage to frequency, voltage to time, and direct compensation. I believe this is actually direct compensation right here. I don't think the author of the textbook put things nicely in perspective here, but anyways, so yeah, the themes for the topics in this chapter is a bit not very well sorted, if I can put it that way. But anyways, that's pretty much chapter 4. What I think I'll do is I'll show you guys, because this thing does crop up a few times in the exams, the successive approximation voltmeter, which is this whole process set up for it. So let's go quickly take a look at that. We'll do another, just thumbs up an example. I also just want to demonstrate to you guys something interesting about that voltmeter. What you guys should note with the successive approximation voltmeter is that with odd numbers, it will go through all 4 steps. Okay, for a 4-bit number, you guys are only going to get 4-bit numbers in this subject. Right, so if we take, for instance, so let me maybe demonstrate this. So if I say the unknown voltage is equal to 1 volt, right, so at the start, our register is going to be set to 0, 0, 0. Then our first step, the logic programmer is going to set the register to 1, 0, 0, 0. So converting this binary number to a decimal number, that's going to be 8 volts. So that means that the reference voltage is bigger than the unknown voltage. So it's going to reset that one. Right, so in step 2, we're going to reset the most significant bit and then set the next one. And we'll see that this is going to give us, I believe this is 4 volts. VR is still bigger than VU. And then step 3, so just, yeah, so for step 3, that's going to be 0, 0, 1, 0, which is 2 volts. So that's still applicable. Reset that 1. That's 1 volt. Okay, so the reason why this happens is because when you convert an odd number to binary, it's always going to be, so if we take a 4-bit number, it's always going to be ones and zeros, but the number will always end with a 1. Right, so an odd binary, yeah, so odd numbers in binary always end with a 1, and even numbers, on the other hand, so for even numbers, this will depend on what value you have. So for instance, if you get given 8 volts, you're going to be done in the very first step. If you get given 10 volts, you will be done in step 3. If you get given 4 volts, like we have here, done in step 2. Or if you get given, let's say you get given 6 volts, you're going to be done in step 3. So that's going to, yeah, so there's actually quite a few things that's going to, that's going to depend on what kind of value you get given. 12, that's going to be up until step 3. I think, no. 12 is going to be up until step 2. So you're going to do step 1 and step 2. 14 is going to be up to step 3. You're not going to have 16 because 16 is a 5-bit value. So it depends. So even number and binary. So if I can maybe just demonstrate. So you can have, doesn't matter, 1 or 0, 1 or 0, 1 or 0, but it will always end with a 0. Okay, so if I can maybe demonstrate here. So let's say VU is equal to 12 volts. Then if we start, and we start at 0, 0, 0. And then the first step, that's then going to be 1, 0, 0, 0, which is 8 volts. So in this case, VR smaller than VU. So let me maybe just scroll a little bit here to the side. So we're going to keep the 1. And then in step 2, that's going to be 1, 1, 0, 0. So converting that, so that's basically 8 volts plus 4 volts, which is then 12. Right, so as you guys can see, 2 steps in this case. But for odd numbers, you're always going to go through all 4 steps.